Hello again. Welcome to the last part of our tutorial. Here we would like to wrap up all the things that we have learned today, and to offer also some perspectives on where to go on from here, while taking a look at some of the trends that we have noticed in the related literature to the topic that we studied today. So first, well, we were mentioning during today's tutorial the different scenarios, use cases, and sources of uncertainty that we encountered in the real world, and how is it important to address them. In the past few years, we are lucky to have seen an emergence of different data sets trying to help people in the community advance in these specific areas. So just focusing a bit on what we've seen in the part of image segmentation and autonomous driving data sets, we have seen different data sets that come up with different weather conditions, like ACDC, where we have rain, fog, snow, night, different variants of cityscapes using synthetic rain, synthetic fog with different intensities of fog. This dark Zurich is a data set with night images, and Vancouver is a data set with rainy images. In terms of distribution shift, we've seen different variants of cityscapes, like cityscapes C corrupted, where you have different corruptions of different intensities. Out of context cityscapes is OC, where we change the context and trying to see how are the predictions flipping to evaluate the presence or the impact of any spurious correlations in the data. For example, here you can see in this data set we replaced the road and the sidewalk pixels with water or with sand, and we want to look for the pedestrians and and the remaining classes that are not changed, whether there was a flip in the predictions or not, which have been caused by this influence of the context. Here we have some images from ACDC, and here from Cityscape C, where you can see we have different types of corruptions to simulate different sorts of distribution shifts. So these data sets, this Cityscape C might not be necessarily very realistic, but it gives us also a measure of seeing when you start drifting just a bit by bit from the original training distribution, how is the performance degrading? Do you see a graceful failure or not? In the same spirit, we have the shift datasets, so I've outlined as the synthetic datasets, where we have a fine transition between night to day or between different weather conditions that we don't have in real data, and this allows us to capture more at a finer level the degradation of performance as we have a continuous distribution shift. Then we have a few datasets with very unusual conditions, wild dash and wild dash 2. With very peculiar objects or roads or data from different continents that were not seen during training. And the recent trend is to have these RoboBev, Robo stands for robust, RoboBev, Robo3D, RoboDev benchmarks, where again the authors propose ways to data sets and benchmarks to assess the robustness of the models as we accumulate different degradations in the input. On the out of distribution side, again, we have quite a few data sets, fish escapes, segment me if you can, that you see outlined here, with different sorts of objects that were not seen during training. Street hazards is synthetic, but it also has interesting objects that are added at test time that were completely unseen at train time, and BDD anomaly, which is a reshuffling of the BDD training data to have a set of classes in the train set that were not in the test set that were not seen during training. In this case, it's motorbikes and trams. We have seen also a surge of data sets with different sources of error in the same conditions. So this is the MOAD dataset, which was released last year at BMVC. And now this year, we finally see an actual unified reliability bench on all sorts of tasks, because the risk that we have with these types of data sets is certainly they're useful and nice, but what they can lead to is to a specializations of the methods for a particular application and setting. And this is the benchmark effect where people compare on the performance, and as the papers appear, they try to outperform the other, and when sticking just to one of these types of benchmarks, the methods get specialized to that. So in the Bravo challenge, the authors are trying to have a collection of all these data sets, in fact, or very similar ones, where a model is trained on one data set and then is evaluated on different settings of distribution shifts, different weathers, different out of distribution objects. Another trend that we see in the literature is that we're starting to see very advanced neural closed loop simulators from real data, in particular Vista, the follow-up Vista 2, and now the very recent Unisim from Wabi, which have the nice property that we can also see the consequence in time of a certain decision, be it wrong or correct or wrong. So this brings a new dimension of studying the reliability of the prediction modules, because we can see if a wrong prediction has led up to an impact or to an accident or to a stop a few seconds or few frames afterwards. So this is a really interesting avenue that I'm looking forward to see explored. I'm just mentioning a few things on the image classification part that we covered a bit less in some of our talks. So even here we see again an emergence of different data sets trying to cover different types of distribution shifts or different types of anomalies. So here we have ImageNet C for distribution shift, ImageNet R, ImageNet A, ImageNet O for different edge cases and out of distribution cases, and then ImageNet V2, which is a different shuffling of the validation set of ImageNet to offer a new view on the how well our methods are generalizing. Models trained on ImageNet are generalizing to other validation sets from ImageNet. And we see actually a similar trend to other sensors, in particular of LiDAR, where people are starting to look at distribution shift at the change of performance when changing from one LiDAR to another, or at seeing the robustness of the perception, LiDAR-based perception, in particular on the Robo 3D, which is from the same line of works as the RoboWeb. So this is actually an interesting outlook, and we're looking forward to see challenges like Bravo, where methods are analyzed on different settings, not just one. On the downside, so what we see in the community is that while researchers are often reluctant to focus on multiple KPIs, mostly because we were targeting what to be SOTA on one metric and a few benchmarks. So it can be easier to frame and to illustrate the properties of the methods like that, but actually does not offer a complete view of the performance of this method and also the reliability and its properties of being amenable to be used in practice. So in essence, while people try to focus on bold numbers, but when you're looking at different types of metrics, capturing the uncertainty, the overfitting, the calibration, the resilience to OD, and so forth, we often have, as we've seen in some of the results that we've reported before, you don't have a one method beats all type of behavior. So it's often a mix of top performance on some metrics, maybe second performance or third performance in some others. But even though this is sometimes more complicated to advertise or to use as arguments for convincing reviewers or the others that our method is useful, actually it allows us to take a different look and more complete view on how are these methods behaving, where they're failing, and actually this can give us ideas on which parts we may want to improve. So this, well, I hope that in the next years people will get into this trend that we have seen already in some uncertainty related papers of reporting different metrics and different data sets and different conditions for their methods, even though they're not always SOTA. Another trend that we see is that with the emergence and the rise of powerful generative models, in particular on the images, we can start thinking on how to use these models to generate new data for testing under harsh conditions or out of distribution conditions or for long tail settings. So here we are using a variant, a special, a stable diffusion with some specialized, localized special aids, starting from this image, and we can start adding people and kids that are crossing the street, and see how is the method behaving here. We can start filling the images with trash and litter on the street, and see are the pixels for the road behaving differently, or flipping predictions because of that. We can also edit the location to add a certain object in a key area in the image. For example, here, this is the image on the road. We add a baby crossing the street, which is rather unusual, and it's quite rare to have in these types of settings, or an old lady that fell in the middle of the road. So this is an immense opportunity to look at better testing data in the first stage. And in the Bravo challenge, we are using some of these techniques to add encrossed objects in the images, unknown objects, and to see how is the method failing, or how is the method, well, hopefully gracefully failing when encountering objects it has not seen. So we can also use these types of techniques to generate data for domain generalization. So here I have an image from a driving data set, and we can change its style or its background to look like Paris. So those that you are here in Paris for ICCV, you might recognize the landscape, even the scooters, the types of buildings. We can also make it look like India, so we can see that, interestingly, the scooters here are becoming actually rickshaws, so kind of reflecting the distribution shift that we have. And also, well, we might not necessarily change the environment, but we can change the weather. So in this case, this is an image again from a driving data set, and we can add heavy fog, or with very low visibility, or we can have heavy snow, and again look at how our method is behaving in the prediction on these, in evaluation on these settings. So as I was saying, that okay, we can start thinking of them for generating more relevant and difficult training data, but we can also think on generating training data for out of distribution and corner cases. So I'm outlining here two very recent methods. One is Dream OOD by Sharon. She in this paper, her team is using stable diffusion to generate samples at the border, at the frontiers of the boundaries of the classifier decision, to imagine some OOD samples that are very tricky and that could be used for training a classifier with the awareness that these images are OOD, and for which our classifier should return a low confidence, while for the in-distribution ID data, these ones, we should have a high confidence. In a similar spirit and a similar vein, but using conditional GANs. So this is a paper from Harriet et al. Accepted at WACV, where the authors use conditional GANs and want to generate, want to train a robust GAN, but then to generate all sorts of weird patterns that are not necessarily seen during training. For example, these bikers flying around the scene, or these traffic lights all over the street, or with unknown objects, well, like animals of different shapes, where you generate these from these masks that are easy to generate in a more semi-automatic manner by perturbing or existing segmentation layouts. We generate images that are then used for training a classifier like OBSNet that we've seen just before, to detect the anomalies and in the failures of the network. So we can look now also at ways to generate better training data for improving the robustness. Another trend that I would like to outline, and that I've mentioned in the uncertainty and ensemble talk, is the emergence of these strategies in the line of model soups for harnessing the power of foundation models that are trained for a really long time and that are very powerful. So we can repurpose them here for improved generalization with low computational cost. So in particular, there's different ways towards starting from a large model to fine tune it on different tasks or different intermediate tasks like here, and then fine tune them on our tasks, and then average them, fuse them in these so-called model soups, where we have just one model that does really good on all sorts of distribution shifts and out of distribution benchmarks. There's of course still some fallbacks of these methods, in particular related to calibration, but they offer a very promising direction of research, and I invite you to check out the works of Alexandre Ramet, who's been pushing quite a bit in this area in the last year. So since I was mentioning of recent foundation models and ways of improving their reliability, another line of methods that are very, very popular right now in computer vision are these vision language models, be it CLIP from OpenAI or Align from Google, where you have an image encoder and a text encoder that has the nice feature of allowing us to put classes that we want to detect on the fly by just specifying their textual description. So getting uncertainty in these cases it doesn't appear trivial in the beginning, but actually we have seen quite a few papers, well, at least two in this year, where the reliability of these vision language models has been studying with different methods to better do the ensembling. And I'm outlining here this weighted ensembling technique, where the authors propose a strategy to do a weighted average of all the configurations of text prompts that we can define in our ensemble. So we are just starting to scratch the surface in this area, and I'm sure that there will be many more interesting methods that will be proposed in this line of research in the next months and year. Finally, to conclude our tutorial, I will use an image inspired by the events that we have in COVID, but also by this nice work of Daniel Hendricks on unsolved problems in ML safety, where he is looking at he's proposing to use multiple layers of robustness and safety barriers. So if you remember, during the lockdowns and in the peak of the COVID pandemic, we often have seen this Swiss cheese model, where we had different layers that were not fully they were not fully protected. They were not at 99%, 99.9% offering protection against COVID. But the mere fact of accumulating them actually in the end offered us a good chance of staying safe. So we had here as a first layer to avoid large indoor gatherings that actually avoided quite a bit of the chances of getting the virus, then keeping social distance and wearing a mask, washing your hands, and so forth. So at the end of the day, well, even though we have some viruses that pass through the holes of the Swiss cheese, given enough layers of protection, we have a decent chance of actually staying safe. So we can think of on the same thing we can visualize in terms of reliability. We can visualize the same type of model where you have different components improving reliability. Here, Daniel Hendricks outlines a few: systematic safety, monitoring, robustness, and alignment. But we can look at also all the techniques that we have seen today, be it uncertainty estimation, calibration, ensembles, data adaptation, domain generalization, auto-distribution detection. So if you start accumulating all these in a system, in a safety-critical decision system, I think this is where we can see the peak fulfillment of all these methods, having them contributing to a safe system. Because well, whatever method we may develop, we may come up with individually, it cannot offer 99% accuracy on all sorts of conditions, on all sorts of unseen conditions that we didn't think during train time. But if we accumulate them in this type of Swiss cheese model, we'll actually will make our ML systems safer. So this is where I will conclude the tutorial, and I'm leaving this as a take-home message to explore to look at all these any of these bricks that compose this Swiss cheese model for safety, or for if you're not working in this area specifically, to take home some of the ideas and some of the problems that we are addressing in this area, and to take them in your communities and look at how are your methods behaving under distribution shift, or how are they doing in terms of generalization to unseen domains or to other domains different from your training distribution to some degree, but also to a larger degree in which we are speaking, in case we are speaking of out of distribution. So with that, I would like to thank you for your attention so far in this tutorial, And I will invite you to contact us for any questions you may have and feedback. We'll be happy to take them. And we'll conclude here. And I'm wishing you. I hope to see you soon in a conference anytime soon. Thank you.